Let me share my presentation. I hope my screen is visible.
Yes, sir.
It's changing, right?
Yeah.
Okay. So please listen carefully. The motive behind this session is just to feed you with the actual challenges whatever we have in terms of space exploration. So this presentation covers challenges from launch to landing on any interplanetary surface. It may be Mars, Ceres, Moon, or any other planet. So in this slide, I have covered major challenges projected for Mars, but most of the challenges are applicable. Like it's very similar to other interplanetary destinations. So this presentation is prepared for American Institute of Aeronautics and Astronautics, like your paper presentation. So I would like to share this knowledge to all of you, so please listen carefully. So the first thing is, so before explaining all these things, can anybody tell me, like, whatever challenges you know, like for example if you are going to Mars, so what kind of challenges we will face initially? If anybody knows, then you can unmute yourself and talk, or else if you are comfortable with chat box, definitely you can drop your text in chat box.
Hello? There's a distance that is the problem, sir, and alongside that, the window between Earth and Mars, which is very short, where the distance is the lowest, is very short. So the launches have to be generally prepared at the moment at this particular time frame. So that is a challenge that we do not have access to Mars exploration all around the year. It only comes regarding certain times, sometimes in that is the problem. Then also our current technological challenges, including propulsion, then fuel, etc. That is the problem.
Excellent. What about others? Keshav, Nandita, Niveta, Manpreet, Sayed, Adava, anyone? Shashank.
सर मेन प्रॉब्लम तो हम उसे कंसिडर कर सकते हैं, हमारे मटेरियल्स वगैरह हो जाएंगे जो
Okay.
यहाँ से इनिशियल लॉन्च। अभी जैसे यहाँ से सही चले गए, वहाँ तक जाने के टाइम पे हमारे फेलियर्स वहाँ पे पता चल रहे हैं, उसकी कंडीशन। दूसरे पे सर ऑर्बिट में, ऑर्बिट ट्रांसफर जो हम करते हैं उसमें टेक ऑफ, ये सब मेन प्रॉब्लम है। प्रोपल्शन तो सर सिस्टम है एक मेन क्रिटिकल फेज का, वहाँ पे जाने का कैसे मैनेज करेंगे, मतलब वहाँ पे पूरा टाइम जैसे लगता है, तो मतलब कैसे 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 किया जाए? सर वो मेरा आ रहा है, मतलब वर्ड नहीं आ रहा।
You are audible, but your voice is breaking. Uh, you are missing the continuation.
मैं सर कह रहा हूँ सर, दिमाग में सर वर्ड नहीं आ रहा, मैं मतलब वो बात है।
Fine, fine, fine then. So yeah, let me explain you. So just forget this content, forget this abstract. So just consider a scenario. So we are on Earth and we are planning to go to Mars. So in that case, we'll be using rockets, spaceships, and some other components, some other vehicles to land on Mars. So just consider this scenario. So if you consider this, then definitely you will figure it out. What are all actual challenges we have? Okay. So in this paper, like in this presentation, I have covered everything. So like we have categorized all the challenges into three parts. First one is earthbound, that is terrestrial challenges, and the second one is interplanetary challenges, and the third one is Mars-bound challenges. Okay. So the third three phases. So let me show you the chart. I hope you guys can see this chart, right?
Yes, sir. Yes, sir.
Yes, sir.
Yeah, the complete challenges I have categorized into three different phases or three different types or categories. The first one is Earthbound, interplanetary space, and Mars. So we are going from Earth to Mars. So these are a list of challenges which we will experience if we go to Mars basically. So terrestrial challenges, whatever we have is like considering feasible future technology, selecting effective mission strategy or mission architecture, and selecting like optimal or good heavy launch vehicles, crew size limitation and optimization, analog habitation system, like analog habitat to train crews or astronauts. So let's discuss more in detail. So this chart is just to outline like these are all challenges which we have, and most of the challenges are very similar to any kind of interplanetary exploration missions. Let's say this one, the center chart, trajectory options for different destinations, and then trajectory correction maneuver, spaceship management, radiation, zero gravity, and in space health issues, solar irradiance, and temperature issues. If we are using NTR, nuclear thermal rockets, or nuclear electric kind of propulsion system, then definitely we'll be having nuclear hazards. And the most important is isolation and psychological effect, which the astronaut will encounter when they travel from Earth to Mars. Then communication system, lack of internet facility, and if we are using conventional or chemical propulsion system, then definitely we'll be having challenge to manage those fuels, cryogenic fuel management, waste recycling and management, extra vehicular activity. So any other planet destination approach, orbital capture, gravity assist. So these are all major challenges which we have. So first one, let's consider the first one, terrestrial challenges. So considering feasible future technology. So right now, we have n number of technologies that can be utilized and executed to send um, astronauts to Mars. Let's say SpaceX, they have Starship, and they can deploy more than 100 people on Mars. If they want, they can launch it by today itself, but they don't have the complete plan what they will do if they land on Mars, the scientific objective, how will they return. So they don't have any objective or scientific plan. That's why they have not executed any human mission architecture, human mass mission as of now. So, so if we are planning to design some mission architecture, let's consider for any destinations. I want to send some 3 to 6 astronauts to Mars, Moon, or Ceres, and I want to design a human mission architecture. So in that case, we need to consider feasible future technology. Can you explain like what is feasible?
I would like to give it a try.
Yes,
Feasible generally within the engineering and technology background generally stands for anything that can be achievable with the current knowledge or uh, upcoming potential research within the next 10 to 20 years of time.
yes, correct. So that's what feasible means. It's in simple terms, with whatever technology we have right now, looking at the trend, whether that technology is possible or that kind of technology or mission can be executed within next 10 to 20 years or next 50 years, anything. Okay, we cannot say that, let's say, for a human mission to Mars, I'll design architecture where we can send more than 10,000 people to Mars. That is not at all feasible, right? So, with the current technology, we can send astronaut numbers up to 3 to 6, that's all, not more than that. So, if we are considering to send more than 6 astronauts, then definitely we have to consider the cargoes, the food requirements, the water requirements. So everything we need to consider. In that case, mass will increase. The launch mass will increase. The mission cost will increase. So that's why it's very important to underline or to highlight feasible technologies that can be used or utilized in any sort of architecture, human mission architecture. And the second point is mission design and architecture selection. So, so far, more than 50 to 60 human mission architectures have been proposed, especially for Mars. You can just see the list here, the top list here. Inspiration Mars, Mars One, SpaceX Mars Transportation System, Mars Base Camp, Mars Semi-Direct, Mars Society Mission. So from Inspiration Mars to 90 days study report proposed by NASA and their mission cost in terms of billion USD dollars. I hope everyone can see the graph, right? The graph.
Yes, sir.
Yeah. So we need to select perfect architecture that can be executed, and also we need to select cost effective architecture. So these are all things we need to consider in mind before proposing any kind of architecture or writing articles on any kind of architecture or human missions. So that's the second point. And the third point is considering heavy lift launch vehicles. I hope I've already stated the same point. If you take India, the PSLV or GSLV, whatever rocket we have right now, the advanced rocket, we cannot deploy huge masses to any orbit, and they aren't capable enough to deliver that kind of masses. In that case, we need to consider heavy lift launch vehicles, like optimal launch vehicles. If you see this chart, you can you can simply say like which rocket is capable or which launcher is capable enough to deliver huge cargoes. Here we have the list of rockets, and here you can see the payload delivering capability in terms of metric tons. So from this chart, can anybody comment? So which launcher is capable to deploy human missions to Mars? So if you answer, I will analyze you like how you guys are thinking, looking at a chart or a map.
According to me, none of them.
I'm sorry.
I don't think any of those rockets can take us to Mars.
Okay. So which one will be good? Like which one will be more effective in terms of
Uh,
cost?
I'm in
Cost
terms of I think the
it is
Starship or the Saturn V are the closest ones that can take us.
good. So Saturn B is retired right now, so we don't have technology or facility to manufacture the components required for Saturn B. So either we can choose Starship or Ares 5. Okay, so the launch cost, reusability, and payload delivering capability of those rockets is very high compared to all other rockets. So this is how you should select good launches for any kind of mission you propose. And the fourth point is limitation of crew size. Anybody have any idea? So like NASA in collaboration with Russia, they used to launch astronauts every 3 months or every 6 months to International Space Station. Anybody have counted how many astronauts they used to send for every launch approximately? If you know, you can comment yes. If you don't know, you can comment no. Then I will tell.
I don't know, sir.
All right, it basically ranges from 5 to 6, that's all. Okay, so this is because if they send more astronauts, then definitely they have to send more cargoes. Cargoes in the sense the food required for surviving there and other things, waters, uh, mission components, everything. So as of now, based on Starship and Falcon Heavy rocket, the launch for the cost for launching 1 kilogram of mass to low Earth orbit is almost around 500 USD dollars. Okay, so so this is how you should choose the number of astronauts like suitable for any kind of missions. And the last point is training of crew. So the space environment is new and the destination is also new. We don't know like what kind of temperature we have and what kind of radiation, like what range of radiation dose we will experience, right? And we'll be doing multiple science activities or mission activities in that zero G environment, and astronauts will be isolated for long period, more than 6 months to 1 year or 2 year, right? So before sending astronauts to that kind of destination, they have to undergo analog training. So you can see this image. This is Mars Desert Research Station, proposed or executed by Mars Society. So every 6 to 8 months, they used to send 5 to 6 astronauts to this hab just to train them in an effective way, like so that they can survive on Mars with respect to that extreme environmental condition, temperature. So everything is simulated here. So once you enter this habitation system, so you will experience not full zero gravity, but gravity lesser compared to Earth, and the temperature thing. So everything is simulated, artificially simulated, just to train them how to survive on any planets or destinations. So these are all major challenges we have. Anybody have any questions in this slide, especially?
No, sir.
Okay. So if I were in your place, I would ask a question like, so we are having good analog habitation system to train well before sending astronauts to any destinations. Then what kind of challenges we have in that case? So definitely, I say that you can read papers, Mars 500, like 500 days mission, analog mission. Sometimes that report may go wrong. So whatever results we get through analog training, through any sort of analog habitation system, we cannot say that the result or the outcome is very similar, because we are having this kind of analog habitation system on Earth, and here the temperature condition is different, pressure is different, and the radiation dose which we experience is also different, right? That may not give accurate results or effective results in terms of space missions. Am I correct? Am I right or wrong? Any response? See, the thing is very simple. We cannot launch more than 50 or 100 astronauts to International Space Station to train them on orbit itself. So that's why we are using this kind of analog habitation system. Am I audible? Am I audible? Am I audible now?
Yes.
Yes, sir.
Okay. Can anybody tell like when like where I left?
You were just going to explain us the challenges.
Yeah. See, the thing is, so the complete environment condition on Earth and orbit is completely different. That's why NASA is sending astronauts on a frequent basis to train them on orbit itself. So if we take that opportunity, it's not possible for us to send more than 50 or 60 number of astronauts to International Space Station for better training, right? So that's why we are having analog habitation system or analog habitation like have on Earth to just to train astronauts. So that's what challenge is. The result may not be accurate, but somehow we can compare the results. So these are all major challenges which we have on our Earth before expediting any kind of human missions. Am I clear with these points?
Yes, sir.
Now let's move to the second category, earthbound challenges. Now consider we have done all the groundwork and we have launched some six astronauts to low Earth orbit. So after reaching the orbit, so what kind of challenges they'll be facing or we'll be facing overall? The first one is hazard of space debris. So if you compare the amount of space debris from 1970 to 2025, so we have a bunch of it's like a mesh that covers Earth. Like you can see the image. Like it's very similar to this. So if we are launching larger launch vehicles, let's say Starship or Ares 5, so there are chances any debris may come in between and can collide. So that will result in blast or entire mission destruction, right? Anybody have heard or read about space accidents? Like when the rocket reaches the orbit, it collides with space debris, and it creates more debris as well as space blast.
Didn't hurt till now, but it's quite, but it can happen or it has happened. I don't know because I heard that some of the space average that rotates that travels with the speed of 1700 meter per second. So
Mhm.
that can destroy anything that has a capability. So it can happen. So I don't know about any accidents
Yeah,
currently.
yeah, yeah. So there are incidences. I don't remember exactly. So there is one institute in United States that used to track every tiny objects in the orbit. and they used to name every debris with some number. So, if you take SpaceX, if you take India, if you take any space agency, before launching their launchers, they have to report, they have to submit a request like debris clearance report uh, to that tracking agency. So they will tell like if you are launching on this date, whether you will be having interference or not, debris interference. If not, then they will go ahead for launch. If yes, they will postpone the launch. You can just check it out. This is how the protocol works. So right now we are dealing with smaller missions like launching nano satellites or medium sized satellites, right? So in that kind of mission we have lesser risk, but in case of human mission we have larger risk because we are having massive launches where the heat shield, the front nose cone of rocket is the size of nose cone is large, right? So definitely we'll be having the hazard of space debris. So that's what the first earthbound challenge is. And the second one is spaceship rendezvous. Can anybody explain like what is this or what does it mean? From the image itself, you can explain.
Can you repeat the question, sir?
So what is spaceship rendezvous?
Oh, it's just spaceships, if they rendezvous, generally is a point where everyone meets. So if a spaceships or launch happens and some of the parts they go apart, so there will be a particular point or a vehicle where all these what is this parts that have separated will come back and join together on that point.
Yes,
So generally spaceship rendezvous will be uh, is also hinting towards the same, whether rather than a point it is a spaceship in this case.
yes, correct. So if you take space shuttle program, whatever mission they have launched, so at that time they used to dock one spacecraft with another spacecraft, especially the space shuttle with International Space Station manually. So manual docking, they have executed manual docking option. Right now, NASA and other space agencies they are using um, radio detection and ranging like that radar thing, and in future they'll be working on lidar, light detection and ranging. Like they'll be using some sort of laser to coordinate or align themselves for automated dock. So in case of a human mission, we have to launch like n number of components for successful docking and orbital construction, right? In that case, manual option or manual docking won't be effective. So, so here the point what I want to mention is we need to work more on this spacecraft docking technology, like what kind of technology we can propose for effective docking without any miss. So this is one challenge. You can work on this area as well. And the third one is on orbit refueling. So you would have seen like the videos uploaded by SpaceX, like launching two Starship, then fueling in orbit. And you have seen the video.
I have.
Yes. So the challenge associated with this on-orbit refueling is the space same. The space temperature is different. Space the pressure condition is different. So there is no gravity. So we need to maintain the fuel and dock the spacecraft effectively for successful transfer from one spacecraft to another spacecraft without any leaks. So after SpaceX, there is one more company in India called Orbitate. So that works on this on-orbit refueling concept. So Orbitate is planning to refuel spacecrafts rather than larger spacecraft or spaceships. So like Starship and all. So this is third major challenge. And the fourth one is recycle and reuse technology. So apart from SpaceX, can anybody tell any other space agency has any kind of reusable technology in terms of launchers or satellites?
I know of some of the launchers for launches. I do not exactly remember the name, but there are multiple of these small launchers from countries like New Zealand, even in Europe. I forget the name of the companies of these, but I'll try to find them out.
That's really great. Apart from launchers, um, what about satellites? Can space agencies recover and reuse the same satellite once again?
Yes, Northrop Grumman.
Actually, no. Like once the satellite is launched, if that is dead, then they'll be disposing spacecraft either through this re-entry and burn systems. So we need to work more on this recycling technology. So if you take any satellites, so we are incurring and we are investing huge cost to build that satellite, right? So if you take any semiconductor material, like if you take any type of metals, let's say battery, we have titanium metal, and we do have gold coatings to avoid spacecraft from external radiations. So we have very precious metals on board satellites, right? So we need to find out, or we need to innovate some new technology through which we can recover satellites for reusing. So this is what the major challenge we have. Am I right?
Yes, sir.
All right. So the next thing is on-orbit construction and assembly. So like this is connected to spaceship docking. So automated docking is effective rather than like manual docking. And so right now, if you take International Space Station, so all the servicing activities, restoring activities, or any kind of extravehicular activities is performed by astronauts. So they walk out of their cabin and then do all the services, then they'll check in once again. So in that case, we cannot put any astronauts on at risk while construction of massive spaceship in terms of human missions. In that case, we have to innovate robotic technology that can use or that will use its arms to dock every component effectively for massive constructions. So these are all areas where we can work to innovate something new. Okay. Uh, the next thing is earthbound challenges like continue. The next thing is like optimal delta velocity is very significant for faster transit and safe orbital insertion. So I hope somebody like most of you are from aerospace background. So I hope you guys know what is delta velocity, right?
No, sir. Can you explain about it?
Like for example, initially if we deploy a satellite around the orbit of Earth, if you want to change its position from
So it's
lower orbit,
changing.
it's change in initial velocity like final velocity. So that's what we call delta velocity. Let me explain you through this process. Let's say we have launched some satellites and it's orbiting around this Earth. In order to raise this particular satellite from this orbit to another orbit, so we need to push it with some external force like some propulsion system. So the change in initial velocity to final velocity is called delta velocity. Like raising a spacecraft or satellite from one orbit to another orbit.
Yes, sir. Got it. Thank you, sir.
Yeah, so delta velocity play a crucial role in the determination of transit time, the overall time that takes from to reach from Earth to Mars. It's approximately 6 to 9 months. It depends on velocity, delta velocity, at which uh, we throw or insert the satellite into trans-Mars orbit. So that's the major challenge. So like I've already stated, like if we use Polar Satellite Launch Vehicle or GSLV rockets to send satellites to Mars, that is not at all possible. So in case of Mangalyaan, if you take, they use the same rocket. In addition to that rocket, they used gravity assist. Using Earth gravity, they raised the orbital velocity of spacecraft to raise it to higher orbits so that they can inject that spacecraft to trans-Mars orbit. I think you would have seen the animation video, like how they have raised the orbit. If not, you can just check it out. Like videos are available on YouTube. And the next thing is trajectory classes. If you take Mars, we have two classes. One is opposition class and conjunction class. You can just note it down. You can refer it later. So these two classes depends on the planetary position of Mars and Earth. And the same category, the same challenge is applicable for all kind of missions. For example, if you want to send astronauts to Moon, so in that case also we have to consider the planetary position. Like for Moon, we don't have to consider. Like if you take any other destination, let's say Ceres, you have to consider the planetary positions. So which time is optimal for launching any kind of human missions? So that term usually what we call as launch window. For Mars, the launch window opens up every 2 years. So you can just note it down. Some terms may be new for you. Some terms maybe you would have gone through. New terms you can just note it down. You can just refer it later. If you don't understand, just reach me out. I'll explain. So these are all earthbound challenges we have discussed so far. Now the important thing is interplanetary challenges. Anybody want to comment on this topic or point?
Uh, I don't have much to say as I have not been very accustomed to the subjects of orbital mechanics or spacecraft dynamics, but these are some two of the most important subjects if we want to talk about interplanetary alongside satellite trajectory and then space radiation and stuff like that, as these kind of things affect the all our efforts in space the most.
Mm-hmm. Okay, fine. So let me explain you in short. So let's say now we have successfully injected a spacecraft or spaceship into trans-Mars orbit, and now the spacecraft is traveling from Earth to Mars. So the first challenge we will encounter is trajectory correction maneuver. So what does it mean? We cannot say that the spacecraft will remain in the same trajectory for which we have planned. So the gravity of Earth, the gravity of Mars, and the solar flares that can divert spacecraft from its initial trajectory to some other trajectory. In that case, we have to align or we have to correct its trajectory to its original path for successful travel, right? So that's the challenge. For smaller spacecraft, we can use small thrusters to balance its position. But what if we use the same small thrusters for larger spaceship? So that's not feasible, right, to correct its trajectory. So in terms of huge or massive spaceship, we do have this challenge, trajectory correction maneuver. I hope you guys got my point.
Yes, sir.
Yes, sir.
And the second thing is space vehicle management. So, as you guys know, initial travel time from Earth to Mars takes around 6 to 9 months. We cannot say that the spacecraft health will remain same for the entire transit period, right? The radiation may cause damage or rupture to electronic components. The solar flares or solar radiation can cause damage to solar cells, right? If we have some smaller meteorites or smaller asteroids, so asteroids basically, if that collides with any spacecraft uh, component, that can create holes. If you have fuel tank, it may cause a fuel leakage, blasts, any kind of mishap may happen, right? So in case of massive spacecraft, we have to innovate newer technologies, automated newer technologies that can be used for automated vehicle management and space health, like spaceship health management. You got my points?
Yes.
Yes. And the third one is interplanetary radiation and microgravity. So we cannot say that the intensity of cosmic radiation or space radiation will remain same at every point of the space. So the level of radiation around Earth is different, the level of radiation around Mars is different, the level of radiation between Earth and Mars is different. I'm talking about the radiation dose levels in terms of millisieverts, right? So we have to design some insulation or shielding technology that can shield astronauts from all kind of radiation at any points of space. So that's what challenge we have right now, and we need to innovate some materials that can safeguard astronauts from external space radiations. Okay, so that is third point. And levels of delta velocity for various trajectory. Yeah, so if we talk, a trajectory is completely entire like different subject. If you take Mars, we have a conjunction class Mars trajectory, and opposition class free return trajectories, direct mission trajectories. For every kind of trajectories, for every type of trajectories, we have different delta velocity levels. So if we have optimal delta velocity level, then we can successfully inject or successfully make our spacecraft to orbit around Mars. If our delta velocity is high, then we may miss Mars orbit and the spacecraft may enter interplanetary space. So that will result in mission lost or mission failure. So that's also a challenge. And the next one is nuclear hazards. So as I stated, if we are using nuclear thermal rocket or nuclear electric propulsion system, so radiation, definitely we'll be having radiation hazards. In that case, we have to design our spaceship in an effective way so that we can keep astronauts from this nuclear chambers. So that's one type of challenge. And the next thing is isolation and confinement. So what if I keep you guys uh, in a separate chambers for 5 to 6 months? What will happen? So you'll be having all the facilities within that cabin, like food, water, everything. But you have to stay alone for 5 to 6 months. What will happen?
Loneliness and mental health sickness.
Yes, definitely. So the same kind of challenge astronauts will encounter if they are going for a longer trip missions to any destinations. In that case, we need to identify or we need to innovate some good technology through which we can engage themselves to avoid this isolation issues. Right, so these are all like major challenges which astronaut will encounter if they are going for any kind of interplanetary missions. Am I clear with all the points? Any doubts here?
Yes, sir.
Okay, fine. So let's move to another slide. So this is continued. So the next challenge is communication and interplanetary internet. So definitely we have communication lag. So if you take the communication lag from Earth to Mars is it's usually around 13 to 26 minutes. For uplink it's 13 minutes and downlink another 13 minutes. Totally 26 minutes for uplink and downlink transfer. Can like through this communication method can any astronaut engage with their family members on Earth in real time, like how we are having chats, video calls.
It can be between space station and then not with the family. It's not easy, I guess.
Not easy. Like there'll be huge lag. Let's say from Earth you are
Just
sending.
like, say, just like Sunita Williams, right now she was stuck there, so she was just used to communicate with the headquarters of NASA from ISS, most probably.
So just considering that isolation challenge, so we need to innovate some effective communication method through which we can reduce the lag, time lag, or to engage astronauts with their family members and their colleagues, to engage themselves. They can communicate, they can interact. So that will eradicate that isolation issue, right? So that is one thing. And in space, there is no internet. There is no internet access. So here on Earth we are having internet. So we are connecting with people through social media, emails, and we are having Google, YouTube, Netflix, and some other platforms to entertain ourselves. So what about astronauts if they go for longer missions? So that's no option. So we need to think like how we can provide effective communication system to them and how we can provide internet access to them. Like how Starlink is working right now with the constellation, they are providing high speed internet across the globe. So these are all challenges. These are all actual challenges we have right now. So these are all areas where you can work seriously to innovate something new. Okay. And the next one is fuel management. The same thing. Apart from orbital fueling, so we are if we are on a way to Mars or any other destination, definitely if we are using chemical propulsion system or chemical thrusters, so we have to maintain the fuel for the overall mission period. So that's difficult, right? So either you can innovate some technology to manage the fuel, or you can provide some alternate options that we can use for that we can use for um, alternative propulsion systems. So that is one thing, and the next thing is like space-based recycling. So right now, if you take International Space Station, whatever waste they have, so they used to collect in a space bag, and they used to dispose to Earth orbit. So that is the primary like disposal method they are using about International Space Station. So what if, like in the case of human mission to Mars, for every for every kilogram, so we incur cost, right? So we need to sort out some solutions, like how to manage all this waste. So that's also one of challenges. And the next thing is extravehicular activity. Anybody have seen videos or live coverage from International Space Station performing this extravehicular activity?
Yes, sir.
Yeah. So, like what are the challenges we have in terms of this activity, basically? See, it's very simple. The same concept. If a small asteroid comes, if it collides with any astronaut, it may rupture or it can cause puncture to spacesuits that will evacuate oxygen levels. So that is one thing. And in any case, any space debris in orbit collides with the rope, and that can cause the astronaut to flee in space. They can't come back because they have lesser fuels and smaller thrusters to align or push themselves to get back to the space stations or any spacecraft. So that's also a challenge. So you can work on this area as well to provide some innovative solutions. And the next thing is Mars approach and orbit capture. So, so this point is very important. For example, if we are deploying a satellite at 5.4 or 6.1 kilometer per second, so this kind of satellites are optimal. So we can control and safely inject the spacecraft into Mars orbit. So in case of human mission, just to drop down the travel time, so we'll be having higher delta velocity, right? In that case, it's very important to reduce the delta velocity while approaching Mars so that it can safely orbit around Mars. It can, um, like, we can inject the spaceship into Mars orbit safely. So that is important. Okay. So in that case, we need to use opposition or opposite thrusters. For example, if this is spaceship, so here we have thrusters to push it forward. So once it reaches Mars, if the delta velocity is high, then we have to use thrusters at the front end to reduce the velocity so that we can safely inject the spaceship around Mars orbit. Am I clear?
Yes, sir.
Yeah, and the last thing is asteroid impact at Mars orbit. So since Mars is located very near to main asteroid belt, so there are chances we may have potential asteroid that can create impact or collide with the spacecraft for possible damages. So you can just work on these areas like to sort out some solution or to provide some new solution to which how we can address all these challenges. Am I clear with these points?
Yes, sir. Yes.
Okay. Now Mars bound challenges. So now the scenario is the spacecraft has successfully reached Mars orbit. Okay. Now on like at Mars orbit, what are all challenges which we will face? First one is the cosmic radiation, the same thing. Asteroid impact, communication interlink from Earth, the communication lag, and I hope you know as we move away from the center of solar system, the intensity of solar radiation or the solar light decreases, and that can cause power degradation through solar panels, right? So that's also a major challenge. And yeah, in case of human missions, they have to perform atmospheric entry. In that case, we need to provide real-time data of Mars atmosphere and environmental condition, how the environment is, what's the wind velocity, what's the temperature level, whether it's a good time for entry or not. So since we have communication lag, it's very difficult for us to provide real-time data to astronauts for performing all kind of entry, descent and landing activities. Am I clear with this point?
Yes, sir.
See, let's say if you take Earth, so we have satellites in orbit and we have very less communication lag. If any astronauts want to land, so we need to work out simple solutions. So Mars is far away from Earth, right? So since we have communication lag, let's say the spacecraft is entering at some certain velocity, and let's say the wind speed on Mars is high, that can divert the spacecraft to land on other destination rather than targeted site, right? And is it possible for us to send this immediate information to the astronauts within present in that capsule? In real time, it's not possible, right?
No, not at all.
Yeah, so that's the challenge. And see, if, from this image, if you want to land, if you want to enter from orbit and land on Mars, the time duration usually is 5 to 7 minutes. That's all. So once you enter, within 5 or 7 minutes, you will land on Mars. So we have very lesser time. It's because the atmosphere is very thin, and we don't have sufficient or enough drag force to control the velocity. So if the velocity is high, definitely time will be less, right? So that's why the ideal time, entry, descent, and landing time for Mars is 5 to 7 minutes. You can just check in any papers if you want. Okay, so these are all challenges we have, Mars bound challenges. And the next thing is planetary challenges. So this is especially for Mars. Some challenges are applicable for other destinations. The first thing is selecting robust scientific landing site. It's not like we cannot explore any sites we want. So since we are investing huge cost for this kind of missions, we have to select good scientific or potential sites where we can land and perform scientific investigations to discover something new. So that is important part. And the planetary environment, especially the density of Mars atmosphere, low gravity environment, solar radiation, and the power deficit problems, temperature and pressure. So these are all environment challenges. In here you have to propose some good habitation systems that can keep astronaut alive for longer period. Okay, and then the next point is exploitation of resources or extraction of resources. So here what I would like to add is we cannot simply um, take out samples, let's say rocks or soils with our bare hand. There are high chances we may get back contamination issue. Back contamination, anybody know what is back contamination?
Is it bacteria contamination?
Yes, bacteria or any sort of virulence contamination. uh, we cannot say that um, there are no bacteria on the surface because the environment and temperature condition is different. At that condition, some bacteria may survive, may be there, right? So we need to check, we need to screen every element before taking or handling it with our bare hands. So that is what back contamination risk is. So before extracting resources, we need to screen each and every component or every materials or things. So that's one thing. And navigation and surface mobilization. So if you take Earth, we have global positioning system (GPS). If we simply turn on our location, we can navigate ourselves where we are, where we want to go. This is due to a number of satellites in orbit that provides near real-time data to us. So what what if we land on Mars? We have very lesser number of satellites, right? And we don't have any compass or any other sources to navigate ourselves where we are, where we want to go, right? So that's also one of the challenges, like navigating ourselves or navigate like guiding astronauts to mobilize on the surface of Mars. So that's also a challenge. And the last two challenges far away from our imagination right now. I don't want to discuss. So that is applicable if and only if we establish a settlement on Mars, like ethical challenges, space policy, human civilization, like how we are having administrative systems, different countries, boundaries. So that don't want to discuss right now. So these are all major technical challenges which we have right now. Yeah, and this is just density, solar flux, temperature and pressure map distribution on Mars. You can just see the solar flux, the intensity of solar radiation, the temperature levels on Mars, the air density, what's the pressure levels. Yeah, so that's all for this session. And do you have any doubts or comments? Any feedback from this session?
It was a really nice presentation, sir. But well, it's like a very top level because each one of these topics can be broken down into a presentation of its own. Isn't that right?
Yeah.
So
So
yeah,
yeah, please proceed.
yeah. So basically, what I think is it for me. It was really interesting, but also it also shows how much deficiency and knowledge I have regarding this topic. So maybe something to look at during my free time to do some for more research on this. Yeah, that's all.
And what about others?
Yes, the same here. Just like I didn't knew because I was not answering for many questions. I didn't knew many things about these topics. Even I am from the aerospace background, but due to about the curriculum, so
Mm-hmm.
the so we didn't I didn't get to know about this much in the research field. In the R&D, in the sector of manufacturing, I know very much, but in the space field and especially in the research field of space, so I didn't know about this much. So yeah, I can look into it.
All right. So what I want to comment is if you take India, so obviously like it's becoming a startup hub. So like most of the startups they are working on this manufacturing, designing rockets, satellites, right? So it's time to do something new and to focus um, on this side, especially planetary and interplanetary explorations. So we should
Yeah, we
focus something on this side.
actually most of people are working on R&D sector as well, but due to the lack of funding, they stop working and they majorly focus on what's going on in the market.
See, with the funding sources we have, or like whatever position we are in right now as a UG student or PG student, definitely I can contribute or propose some innovative concept. Like it may be a conceptual work, it may be a hypothetical work. That's not an issue. So we should uh, create the first mark or the first impression, right, for the future technology.
Yes, yes.
So that kind of motivation and objective we have at Acceleron Aerospace. So that's why I wanted to take these sessions in between this research training program.